Welcome to solverfy.
In the given problem, we have an electron which exists in a one-dimensional infinite potential well. The electron is present at a given level n. Now, we do not know what n is, and we need to find out what should be the energy that the electron emits if it makes a transition from n to the next lower level, and we know that the next lower level should be n minus 1. So if electron jumps from n to n minus 1, its energy should reduce, and that reduced energy should be equal to a photon which is emitted. So this is, let us say it is gamma. Gamma in this case defines a photon which is emitted, and this photon carries the energy difference between the two levels. Now we are given certain conditions. The width in this case L is equal to 200 picometers. Now let's write down the wave function of an electron in an infinite potential well. The wave function is given as psi of x, where x is this, which is the one dimension between 0 and L, is equal to root of 2 over L sine function of n pi x over L. This is n. So this corresponds to the wave function of an electron in the nth state, in this state. If it is n minus 1, this should be n minus 1, and then you will also have an n minus 1 here. Now, we see that if this value is equal to 0, the probability density, which is also somehow related, so let's write probability density P as x, a function of x, is somehow related to psi n of x. So when psi n of x is equal to 0, p of x, or the probability, should also be equal to 0. Now we see that this function is equal to 0 whenever sine of n pi x over L is equal to 0. And that is true when n pi x over L is equal to some number, probably k pi. Now k can go all the way from 1, 2, 3, etc., etc., etc. It can keep increasing. Now the problem also tells us that the electron density of the probability density of the electron is 0 at x is equal to 0.3 L and 0.4 L. So P at 0.3 L is equal to 0, and P at 0.4 L is also equal to 0. So now let's put the value of x equal to 0.3 and x equal to 0.4. So we have the condition that n pi x over L should be equal to k pi, which implies that n x over L is equal to k. Now we choose the first value, which is 0.3 L. And we can choose, and we also have 0.4 L. So this automatically gives us the relationship that n should be equal to 10 times of k. If we substitute these two values here for the x, we are led to the relationship that it is true only when n is equal to k. 10 times of k, where k goes from 1 to. So accordingly, a value of n can either be 10 or 20 or 30, but the lowest of this is 10. Probably we can also choose 20, but if we choose 20, you will notice that if we were to draw the wave functions, then if this is 0.3L and imagine that this is 0.4 of an L, they say that the wave function or the probability density is 0 only at these 2 points and it is not 0 in between. So that means the wave function should look something like this, or probably in the negative direction, but it should not go to 0 in between. However, if n is equal to 20, which is greater than 10, they will be wave function will actually go to 0 in between. So in this case, we choose n as equal to 10, which is the lowest. Accordingly, n minus 1, which is the lower level, is equal to 9. So the energy of the photon that is emitted should be the difference between the energy of 10 minus the energy of 9. We write that as h square over. When we substitute the values that we have for L and for M and all the values, as well as the Planck's constant, we get 2.86 into 10 power minus 17 joules. So we notice that the energy of the photon which is emitted when the electron makes a transition from 10 to 9 is 2.86 into 10 power minus 17 joules.